All right. Um, Most recent supernova we've had is in 1987. I was 5 years old at the time. And this is what it looked like. This was the before image. This is the point that we think blew up with the arrow. This is what it looked like afterwards. This is in another galaxy, so it doesn't look as impressive as, say, the 1054 supernova that gave you this crab nebula. Don't know why that's a crab. Flash is essentially from rings of gas starting to glow as the supernova happens. So, whether or not a star supernovas is purely determined by whether that iron core can form. So, high mass stars are the ones that tend to do that. Stuff over about 8 solar masses will lead to supernovas. Stuff lower than 2 solar masses, you get red giants, you get carbon nuclei, but the white dwarf that's left over is basically carbon. It doesn't form heavier elements. Stuff in between can form heavy elements, but will tend to end up as white dwarfs. So you may find as you do research into different stars, you may find that there's different remnants left over. Maybe the white dwarf is made out of a different material. But that's kind of the two processes: the the white dwarf and the supernova. Right? And in summary, right, the low mass stars, hydrogen to helium, and eventually the helium ignites, and when there's shell burning, it's unstable, and a planetary nebula is pushed out, and you have a white dwarf. And all of this is basically the contraction, the gravitational contraction versus the thermal uh, pressure outwards, or the degeneracy pressure outwards. So in high mass star, you get multiple shells burning stably and lots of different elements produced. And eventually, you produce iron, and it's kills the fusion, and you end up with a supernova. Now, uh, there's a good question as to what happens when you have companion stars. Most stars are in binary systems. And we'll talk about Algol here, which is an example of one star expanded and how it affects the other star in the cluster or in the pair, right? And in this case, the binary star, there's a main sequence star that's 3.7 solar masses, and there's a giant star, but it's only 8/10 of a solar mass. Doesn't make sense. Giant stars should be more massive than the main sequence stars that are the same age. These two stars form at the same time. The 8/10 of a solar mass star should be main sequence. And I've given a hint what's going on is the the star that became a giant expanded enough that matter could fall in on the other star, and the other star grew. All right, so the 4 solar mass star was originally smaller, and because mass transferred, you get this weird combination of outcomes. Right? So mass exchange can occur between pairs, particularly if one is a giant and the other's main sequence. All right. Well, that concludes the chapter. That's where I wanted to get to. We had uh, all this. The next chapter is going to be about these remnants, about the white dwarfs, and about the remnants of a supernova.